to everybody and welcome to the third session of the day. Now, this session is devoted to heliosismology, which was one of the subjects close to Chitre's heart. So we have three distinguished speakers spanning three generations of heliosismologists. So, stellar astronomers actually classify the stars in three categories depending on the age. So we have the population 3 or the pop 3 stars, which are the first generation of the stars, which are believed to have formed just after the galaxy formation. Then, of course, we have the population 2, slightly younger, and then, of course, the population 1, the youngest stars. So the same thing applies in heliosismology. So our first speaker is Professor Douglas Gough from the University of Cambridge, UK. He started his research career just around the time when the solar oscillations were discovered in 1963. So he clearly belongs to the population 3 heliosismologists. So he actually laid the foundation for research in this subject. And of course, he has made many important contributions. I'm not going to describe those. I can only say that whatever we do in heliosismology, we find that he had already proposed it a few decades back. So that speaks about him. So of course, he has received numerous awards, including the Hale Prize, which is the highest award in solar physics. And of course, we are indeed fortunate to have him here to talk to us because our stellar colleagues are still looking for the population 3 stars in the distant universe. So over to you, Douglas.
Hello, everybody. As Antia has just said, I've known Kumar for a very long time, 57 years, I believe. We were both students in the same university, in the same department, but we didn't overlap. Kumar left the university formally on the 30th of September, midnight, and I started on the 1st of October. There was no finite interval of time between our tenures, but there was a break, and my university understands the difference between open and closed sets, the details of which I won't go into. As Antia has already said, we have worked together on various things, particularly helioseismology, but since much of that has been in collaboration with others in India, particularly our chairman, Antia, I'm not going to discuss that today in any detail. What I'm going to do is to talk about the many conversations I've had with Kumar and the basic philosophy with which Kumar has operated. And so I want to illustrate that with ways of thinking that I've discussed with Kumar, some of the things in detail, others not so much, but putting across the kind of way he would like to think. And I like thinking that way too. And what I want to stress is that what we have tried to do is reduce scientific issues, to the simplest forms so that we can sort of understand them. Our brains are not sufficiently good to understand really complicated things. We like to put things in a simple way, and we call that understanding. So what I'm going to do is really talk about the evolution of the sun, the main sequence evolution of the sun, which is a relatively simple thing. Within stellar physics, it's one of the most simple things you can think of. And I'm going to do it in very simple ways, some of which are quite old-fashioned. But then Kumar, it is said, was a Renaissance man. He liked to think of things in an old-fashioned way. He liked also to think about the assumptions that have gone into modern calculations and to be reminded of things like that, because sometimes there has been a tendency for people to ignore things that apparently don't matter, thinking that they therefore can't occur. And that, of course, is not science. Science is really about trying to understand what does occur, whether it matters to the questions you're trying to ask or not. So I'm going to talk roughly about the evolution of the sun in the simplest of terms. So I'll start off by just showing you the equations. They're very simple equations. You assume the sun to be spherically symmetrical with temperature T, density rho, pressure P, and you write down a set of equations, which I'm sure you've all seen before, and I won't go into it. The first four equations occur, or all those equations occur in the radiative zone of stars. In convection zones, it's rather more complicated, but the sun, what I'm going to really be talking about is the center of the sun, where the nuclear reactions take place, which is something that Kumar has been interested in all his life, rather than the surface. I'll come to the surface in the end. I first got to know Kumar, in fact, through his work on sunspots, which was his first work, which he did as a student. And so I'll end up this talk with just a statement about the effect on the sun of sunspots. But until then, I'm going to concentrate on the core. Kumar's interest in the core, as has been mine, was looking at the so-called solar neutrino problem, which has been kind of solved. The worst of the problems, at least, have been solved. And we're not that interested in that issue today, but I'm going to raise issues that have been discussed in the pursuit of understanding the structure of the sun. And one of the simple ways of doing that, and so these are the equations, you need to relate, of course, pressure, density, and things like, and the rate of generation of energy, which I've called epsilon here on the fourth equation, and the opacity, which is kappa on the bottom equation. So you have a set of equations like this, and I'm going to assume that roughly that the perfect gas law applies. It's not exactly right, and people doing the best numerical calculations, of course, put in all the details. But just for getting a broad understanding of what happens, we can assume the perfect gas law. We can assume that the mu, the mean molecular mass, is given in terms of the abundance of hydrogen, X, by mass, the abundance of helium, Y, by mass, and then roughly a factor of half of the abundance of all the heavy elements. I say roughly a half because I'm assuming that they're all half ionized. And then rough power law formulae for kappa, the opacity, and epsilon, the rate of energy generation. Mu, I'm going to assume for the time being, is a constant. So one way of looking at it is to assume homology relations. We know actually that the sun evolves roughly homologously. The structure, when expressed in terms of dimensionless parameters, like measuring the amount of mass within a sphere of radius r, is scaled according to the total mass of the star. The distance scale is scaled according to the radius of the star. And I really mean the characteristic radius of the inside, the main part of the controlling conditions in the star, the radiative zone beneath the convection zone. The convection zone occupies the outer 2/7 roughly of the radius, but the inside is where 98% of the mass is, and that's what's determining conditions in the core. The convection zone has a very little effect on that, except for giving us information about what might be happening in the core. So if I assume that the functions of X for mass, pressure, temperature, density don't change significantly as the star evolves, the only thing that does change are the scaling factors, then I can substitute that into the equations of stellar structure that I showed you just now and derive these scaling laws that I've written at the bottom of this slide. One can then manipulate those to eliminate things we're not interested in and learn, for example, that the luminosity of the sun goes like almost the 8th power of the gravitational constant, the mass to the power of 5.5, and in particular, X, the hydrogen abundance, to the power of -5, roughly. And then kappa and epsilon roughly scale as I've written them here. So we see that the luminosity is proportional to the inverse power, roughly the inverse 5th power of the hydrogen abundance. I'm going to approximate that as an exponential, which I've done below. And the sole reason for doing that is that it makes the algebra a little simpler. Not significantly simpler, but it makes it easier to show. And so I'm going to use that. It turns out that if I use the original scaling laws, the result looks more complicated, but numerically it's almost the same. So let's put that in. And then I wrote down an equation for the evolution of the star on the main sequence. In other words, the rate of generation of energy, which is the mass times E, capital E, which is the amount of energy generated by the hydrogen burning reaction per unit mass. And then the rate of change of burning of hydrogen into helium dx per dt. And that's equal, of course, just to the luminosity. And that equation now is very simple to solve. And there it is lower down, that the luminosity as a function of time is that simple formula there, where, and also X, the hydrogen abundance, slowly diminishes according to that rule. There is a formula for alpha, that constant, which I've given just below. It doesn't fit the numerical results quite so well. It fits it rather better if if I recalculate the coefficient beta according to the current hydrogen abundance, and then the value of that factor is 0.4. So I've got a very simple formula at the bottom of that the bottom of that slide, which gives you the rough idea of what happens to the luminosity as a function of time. And the important thing is that you can see it's an increasing function of time. There's a picture of it. The dashed curve, the continuous curve is the one I would have got straight from the homology relations. The dashed curve is just the one with the adjustment of that coefficient alpha. And the asterisks are modern numerical calculations of the evolution of the sun with all the physics that people know how to put into it. And so you see this very, very simple law can satisfy the numerical results to a very high degree of precision. And so it's quite useful to think in these terms for understanding what's happening. And one of the important things to understand here is that the luminosity is an increasing function of time. And the reason for that basically is that the hydrogen is being burned, there's less hydrogen, and as a result of that, per unit mass, there are fewer particles. So through the equation of state, which is pressure is number of particles per unit mass times kT, it follows the pressure wants to go down, the inside of the star will collapse, and as a result of that, as we know, when it collapses, the temperature goes up, and as a result of the temperature going up, mainly the result of the temperature and the pressure goes up, that causes the energy generation rate to go up, and that's why the luminosity is increased. And that's a very, very, very simple, obvious conclusion that you can come from this kind of analysis without looking at all at any of the details. So I should say that back in the 1960s, early 1960s, 1962, there was a wonderful paper by three Japanese scientists, Hayashi, Sugimoto, and Rosshy, who wrote a 200-page paper explaining the evolution of all stars in these very simple terms, because there were basically almost no numerical calculations in those days, no computer calculations. And looking at papers like that, you get to learn, just in the way as we have here, various properties of the star that you really can't change. So the advantage of that is that you can be very sure that this increase in the luminosity is an invariable property of a star like the sun. The an interesting effect, I should say, that once numerical calculations of any physics started occurring, which began really in the 1960s and then seriously and then has improved, the more and more complicated calculations that are made on computers that take longer and longer and much more computing to do has caused people to believe that instead of these very simple arguments. But they're less secure because they're more sensitive to the little assumptions that go into the computer programs that, that people don't think about after a while because they believe that if it comes from an expensive computer calculation, it must be right. And that's not necessarily true. And one example of that I can give you is that back in the early 1970s, with a student of mine, Fisher Dilk, we thought that the sun actually went through a blip in the luminosity. The luminosity dropped as a result of mixing in the core, dropped on a timescale, a very short timescale, a timescale of a mere million years, and asked the question whether this would affect the climate. Climatology has been an interesting subject, and people have wondered why the Earth has apparently been so stable to this variation of the luminosity of the sun, which of course changes the amount of energy coming from the sun onto the Earth. And so I actually persuaded somebody who was involved in running what was then the world's most complicated climatological calculations that existed. It took the world's biggest computer every night to run. And so we couldn't use that computer. This was at the National Center for Atmospheric Research in the United States. And I persuaded somebody to turn down the sun by a few percent to see whether it would cause the Earth to glaciate, because I was very interested in glaciation at the time. And sure enough, he did it, and that worked. Now, that was great. That's what I wanted to learn. But I remember going to work the next day and meeting this man, Svigel Chen was his name, an Israeli postdoc, who came to me with a sort of quizzical look on his face and said he's got some interesting news for me, because when he had started to put the program back to what everyone was doing, he had forgotten to put in the initial conditions of 2 days before rather than the day before. And so the initial conditions were one with the Earth glaciated. And he said he put the luminosity of the sun back up again, and the ice didn't melt. Now, this was related to an issue that had been raised earlier. It had been raised and called, well, I think it wasn't actually called until this particular calculation was done, the faint sun problem. Why was it the faint sun problem? It seemed to me that it was the unglaciated Earth problem, but it was the faint sun problem because people believe this complicated numerical calculation. So surely something's wrong with the sun. If he couldn't, with a few percent change, melt the ice, why isn't the Earth continually glaciated? Because the luminosity of the sun, you can look there, is only about 75, time t equals 0, is only about 75% of what it is today. So the Earth should have been glaciated continuously. And so obviously something was wrong with what astrophysicists were doing. That was the conclusion of the scientists who believed in numerical calculations. But it's quite clear, I hope I've convinced you, that this very simple physics tells you that the luminosity has to increase. So it had to be these complicated, expensive calculations that were wrong. And of course they were. The way even modern meteorology calculations today work is that there are it's a very complicated three-dimensional time-dependent fluid mechanical calculation, which is moderated by observations. But there are various things in that calculation that you don't fully understand. How clouds mix up temperature, how the rain is affecting things. I mean, a lot of at the level of basic physics, these are too complicated to calculate. And so what people do is they parameterize these effects and measure the coefficients in the parameters by flying planes in the atmosphere, doing all sorts of things, measuring it and putting those things as a constant. But we all know that if you're doing a complicated stability calculation, the stability depends crucially on what things are held constant and what are not. And things that are held constant on a time scale of weeks, which is what the meteorologists are doing, are not necessarily constant on a time scale of 1 million years. And so, to me, it's clear that the Earth is actually stable on a time scale of 1 million years, because those parameters that the meteorologists set as constants are actually not constant, but they evolve on their time scale and keep the Earth stable. So here's just an example of where these simple arguments really demonstrate, in my opinion, that some of the complicated numerical things that everybody's so proud of are not necessarily correct. The important thing is to look at what the assumptions are. These are the assumptions that are made for standard evolution of the sun. You don't have to read them all, but there are all sorts of things that are just ignored, like mass loss, accretion of material, no great instability, various things of that nature, which have been put into the numerical calculations. And because we do reasonably well, and I say reasonably well, I mean, some people, John Bacall in particular, would say, well, they did fantastically well in reproducing what we know about the sun, but it's not actually fantastically well, as I'll point out again later. Not that, I mean, he does it to within a fraction of a percent. Well, I know a percent or so for a lot of the variables that he computes, but we have measured by seismology to a much greater precision than that, and the modern solar models don't agree with the helioseismological conclusions to within the errors in the measurements. I want just to show you now, that's just a reminder of the formula that tells you approximately the luminosity of the sun over the main sequence. Some people draw you pictures, they'll draw you complicated curves, but it's as simple as that. And I showed you how well it fits the numerical formulae. And it's very useful to have equations as simple as that, because you can work with them and sort of understand them. Okay, so let's go on now and ask, you know, what else could happen? And this is just an example of what can happen. When people were worried about the faint sun problem, they said, well, look, something might be happening so that the sun wasn't evolving, as I showed you before, according to this. What's wrong with this? Well, I showed you a list of assumptions. One of them is that the constant of gravity, capital G, might have been changing with time. Various people like Dirac have suggested that. And if G were greater in the past than it is today, because through the homology laws, we know that the luminosity increases with the constant of gravity, perhaps you could adjust things to make it look constant. And that, in that picture, I have drawn what we call the total irradiance, the flux of energy coming from the sun as a function of time. The thick continuous curve at the bottom is the one I showed you before, the standard one. And the horizontal curve at 1 is, it looks like a horizontal curve at 1, but it's not quite. It's superposed on another one. And those of you with good eyesight can see that those two curves don't quite fit, but they almost do. And that is produced by assuming that the gravitational constant decreases with time according to a power law in time. And the formula I've used is a power law to the -1. It doesn't have to be -1 because you can adjust it with various different power laws, but a power law of -1 can be adjusted to do that if if the constant, the units in which you measure time, are the units of the age of the universe. So it is possible to adjust things so that the luminosity of the sun is not, that it's the total flux of energy reaching the Earth, not the luminosity of the sun, because the radius of the orbit of the Earth around the sun, of course, has changed too, with the constant of gravity changing, and that's taken into account in calculating that curve. The dashed curve is the kind of curve you would get if the sun was losing mass. And various astronomers have estimated the mass loss rate of other stars and made an estimate of what the sun might have done. And that dashed curve is one such example. And I'll come back to that later. Okay, now this is a picture of the square of the sound speed as a function of radius for the sun for various models. The only ones I want really for you to look at are, first of all, the long dashed curve, which, I mean, the square of the sound speed is roughly proportional to the temperature. It's the temperature divided by the mean molecular mass. And so that is roughly a temperature curve. The continuous curve is a modern solar model after an age of 4.6 times 10 to the 9 years. There are two continuous curves. They're superposed on each other, and you can see that there are two because the thickness of that curve appears to vary as the two curves don't exactly fit. And the other curve is the sound speed as a function of position that is deduced from helioseismological measurements and analysis, subsequent analysis. What I want to point out is that what's happened with time, the dashed curve is time t equals 0. The continuous curve is time roughly the current age of the sun, is that what has happened is that the sound speed has dropped in the core. And that's something that I mentioned earlier. The reason it's dropped is because the helium abundance, the hydrogen abundance has dropped, the helium abundance has gone up, the mean molecular mass has gone up. And so that reduces the temperature. And so that causes a variation in the sound speed. It's really the sound speed that helioseismology is working with. And so what has happened, in fact, is that helioseismology is telling us that, and measuring those conditions very near the core is telling us roughly about what's going on. And one can try to measure the amount of helium that's been produced, the amount of hydrogen that's been lost, because that's related to the age of the sun. And one interesting thing is that can we take these complicated numerical models and use these arguments to calibrate them to try to get a measure of the age of the sun? We know, for example, the age of the oldest meteorites. One presumes it's very likely that the sun can't be younger than that, but is it significantly older? A lot of people studying the formation of the solar system think that it would take less than 1 million years. Some say it will take 10 million years. Could we measure the age of the sun sufficiently accurately to know whether there is a significant difference between the age of the sun and the age of the oldest meteorites? So one thing I want to show you is what we're actually measuring. This is just a ray diagram. It's a picture of the direction that sound waves travel when they propagate into the sun. They get refracted near the center because the temperature is going up so rapidly. And the angle with which the ray leaves the surface of the sun, it is a measure of the direction of the wave number, which depends on the frequency and on the horizontal scale. But since it's sound waves, it would be useful actually to redraw that picture, where instead of having physical radius, which is what's happening here, we have essentially what I call the acoustic radius, that is a measure of how long it takes the sound to travel. And in that case, that's exactly the same picture, rescaled. And you can see that almost all those rays look to be almost vertical and very straight until they get very close to the core, and then they deflect around. And so the rate at which they deflect around, the details of that, depend crucially on this angle with which, I realize I can, no, I can't, depend on the angle with which, the angle of approach. And so by measuring conditions of that angle, one can learn about the details of the interior. And that's how we do that. And that's basically how we measure the amount by which the sound speed varies in the core. When the calculation is done numerically, we assume still a spherically symmetrical sun. And so we've got a wave equation. It's a complicated wave equation, but the wave equation has separable solutions in the form that you would get even with the sort of sound waves in a simple sphere on Earth. It's multiplied by an e to the im phi, where m is the angular order of the wave, a Legendre polynomial, and then a function of radius, which has wiggles in it, and the number of wiggles is a measure of the vertical wave number. The horizontal wave number is determined by the degree of the spherical harmonic, and that's little l, it's an integer, but as in all problems of this kind, the important quantity is not little l itself, but the square root of l into l plus 1, which I'm calling capital L. This is now a formula for the frequencies, an asymptotic formula for the frequencies of waves that are that have a low value of L compared with the vertical wave number, so that they're traveling almost vertically, as you saw in that picture. And it depends on a quantity nu zero, which depends on the sound travel time from the center to the surface, and other coefficients, all those coefficients, epsilon, and then A, B, C, D, E, F, G, etc. They're all constants of the equilibrium model. The thing I want you to see is the dependence on the capital L, because it's only near the very core of the sun that the value of capital L actually matters, because it's the capital L appears to be almost zero further out, as you could see from that ray diagram picture. And so it is just the constants of the highest powers of L that determine the structure of the core, namely capital A, capital C, and capital F. And those quantities can be written asymptotically in terms of the sound speed according to that formula at the bottom. So you take various powers of the sound speed and you differentiate it by a certain number of times. And that gives you a formula for the coefficients, capital A. The capital A is an integral, and this is the integrand that I showed you at the bottom. I should have written that down, but I forgot. So it shows the integrand for the coefficient capital A at various times. The solid curve is for a model of time today. And then the other two curves are half a gig a year younger and older. So there isn't that much change, but we can measure that. We can measure that extremely precisely. And you can see that it's only in the very core that those curves deviate. And right throughout the rest of the star is pretty well the same. And so that really does demonstrate that when we measure that coefficient in that asymptotic formula, we really are measuring conditions in the center of the sun. This one is the values for a model of the sun of current age. And those are the coefficients for the coefficient A, the power of L squared, which is the continuous curve, which I've just shown you, in fact. And then the other two are for C and F. They're less sensitive to variations, but it's extra information that we can use to calibrate the age of the sun. And if we do that, we can get an age. But before I show you that, I want to write down what I think is still the oldest meteorite that's been measured. There's its number. And the age is 4.5682 gigayears. that is a limit that we might well believe the sun has to be at least that old, because it's hard to believe that that comet, that meteorite, sorry, is older than the sun. So most people will tell you, of course, the sun can't be younger than that. Okay, now let me tell you the results of calibration, a calibration that I did with my postdoc, Günter Hudeck. And it looks a bit complicated. You don't have to read all that stuff, really. We were trying to measure all sorts of things. The first column just tells you which of the parameters we were measuring. A, C, and F were the ones I showed you in that asymptotic formula. There's another formula, which I'm calling changing gamma. That is something to do with ionization near the surface of the sun, and is required if you want to also measure the structure of the convection zone, but we're not interested in that in this talk. So I'm just looking at what happens when we take different values of A, C, and F. And I've calibrated two different models with slightly different assumptions so that we can get some idea of the sensitivity. And you see that all the numbers for the age, 4.60, something fairly small, is what they always get. And so that appears to be the best we can do at the moment with modern physics doing the best calculations to get an estimate for the age. And that note that 4.6 is comfortably greater than 4.57, which is the oldest meteorite. So at least it looks as though the sun might be slight. Oh, I see, I've written it at the bottom again. Looks as though we're on the kind of right track. But have we got everything right? Maybe not. And so let's just look back at that formula that I gave you at the top. One could integrate that formula with time to get the total amount of energy that's been produced over the age of the sun. And that's 0.84 times what it would have been had the luminosity of the sun been constant. That's just a result of a simple integration. But note that what that's doing is measuring the amount of hydrogen that has been converted into helium. And so if the luminosity of the sun had been constant during the main sequence evolution, because, for example, the gravitational constant had been decreasing, then because we've measured basically how much hydrogen has been burned with helioseismology, we would have to reduce the age of the sun to 0.84, which would be 3.9 gigayears, which is less than the age of the meteorites. So if you really believe that the meteorites were formed after the sun was formed, or certainly not before, then that rules out the possibility that the gravitational constant was changing like t to the -1 in units of the age of the universe. One could find a slower variation, but then that variation, if you insisted, and don't forget, the value that Günter and I got, 4.6, is a bit bigger than the 4.57. And so you could say that puts a limit on the rate at which the gravitational constant can be decreasing. And that would involve reducing that power of t to something like 1/40th of what it was before, which is tiny. Here I've shown you again the picture I showed you before with the dashed curve. The dashed curve giving you mass losing. That had a much higher luminosity at the very early stage of the evolution of the sun, but that didn't produce a great deal of extra hydrogen lost. And in fact, that reduces, if that were the case, it would reduce the age of the sun to, I can't remember the exact number, but 4.59, I think, which is still older than the universe, than the oldest meteorites. And so therefore, that possibility still remains at the level at which we're talking now if we don't think about all the other mistakes that we might have made. But I want to talk about other mistakes we might have made. First of all, we have evolved the sun to the current luminosity. And the luminosity is calculated or estimated from the total irradiance that we measure arriving on the Earth, taking into account, of course, that the orbit of the Earth is not exactly circular, but you take that all into account. And that gives you a value. And the IAU actually have now got a value that they are. Oh, sorry. All I wanted to say here is that with a mass losing model, for example, and also with the constant of gravity changing, one does have to change the formula which is being used for integrating the output. I showed you the very simple formula when the mass was constant and the constant of gravity was constant. In this case, I've just shown you that from the scaling laws, the homology scaling laws, we have to have this factor of m in front of the luminosity, which with a coefficient of about 5.5, and that increases the complexity of the final formula you get, but you can still do it. And the same with gravity. There's a factor of gravity that comes in as well, and you can do that, and that's how these calculations were performed. But this is the value I was coming on to next, the nominal luminosity, as the IAU call it, of the luminosity of the sun, 3.828 times 10 to the 26 watts, which is based upon a total irradiance of 1,361 watts per square meter on the Earth when it is at its average distance, well, its distance of 1 astronomical unit, which is sort of its average distance from the sun. That is the sort of number, that is the number that went into, that goes into these calculations. And that's the number that one might even ask, is it right? And I'm suggesting that it's not quite right. One should ask that question. It's the kind of question that Kumar and I would be discussing when he came to Cambridge, and we used to have lunch together every day, discussing general problems. And this is the kind of problem that we will be discussing. Is that number right? It's based on a lot of very complicated calculations, but calculations and measurements, but is it correct? And I want to show you just a picture of the sun now. This is a white light picture of the sun, and you see it's got lots of dark spots on it. Well, I'm showing you this because this was Kumar's first love. His PhD thesis, written in 1965, I think, was about structure of sunspots. When I became a research student immediately after he, I was interested in the effect of magnetic fields on convective stability. And so because it is believed, and well, we all believe it now, that those spots come from an inhibition of convection due to concentrated magnetic fields.
Douglas, we are running out of time, so can you wind up, please?
Okay, yes, in that case I will. All I'm saying is that affects the luminosity of the sun, and I'll quickly go through some pictures. These are measurements of the luminosity of the irradiance, and I told you the number was 1361. That's at the bottom there. The irradiance goes up and down because of the sunspots coming and going, but it's not just the sunspots, because the regions of greatest luminosity, or the regions of greatest irradiance are when the sunspot numbers are the greatest. And the reason for that is that associated with the sunspots are prominences and faculae and things like that, which are bright. And that brightness, which you couldn't see on the white light picture, exceeds the dimming by the sunspots. This is an example. This is taken in H alpha, and you can see these bright regions. You can see dark regions as well, but the bright regions look brighter near the edge because the prominences and the faculae, here's a prominence, they come up way above the surface of the sun, and they radiate mainly horizontally. And so they show up at the limb. And there is a picture of sunspot from Hinode, a spacecraft Hinode, the sunspot receding. This is increasing. These are taken increasing in time. You can see the dark sunspot and the faculae around it. And as the sunspot gets to the limb, because the sunspot is lower than the rest of the surface of the sun, it disappears, and yet the brightness does not. And that brightness actually exceeds the dimming by the sunspot. So this is just a theoretical picture of having this bright region sticking up like a simple cylinder. And when you do that, you can estimate from the measurements of faculae what the irradiance would be. And so the top picture is the one I showed you just now. The one underneath is the simulation based upon the observed faculae. And that looks very, very similar to the one above. It fits very well. But of course, having got that far, you can say, well, all right, but I think I have to go back a moment. This is a typical picture where you can see the stuff around the edge, but it's only near the equator. And that's because the sunspots are only near the equator. And the IAU value for the luminosity is based on the assumption that the sun is spherically symmetrical. Well, it clearly isn't, is it? And if you're looking at the sun from the poles, you'll see that these faculae at the limb, which is the entire equator. And so the luminosity will be greater than what the IAU think. And indeed, if you do that calculation by the same method as was done for calculating those blue curves, you end up with a luminosity of the sun as about 0.15% greater than the IAU value. Well, that's not very much, but the amount by which it differs from the IAU value is certainly greater than the limits that the IAU put on the four figures that they print. This gives us a revised age of the sun. The luminosity is higher, and so the sun will be a bit younger. And if you take the calibration of 4.602 that Gunter Hudek and I calculated, if you increase the luminosity by the number I've given you above, it comes to 4.596. Still greater than the age of the meteorites. But the difference is, the difference from looking at things like this is actually greater than the kinds of times that people studying the formation of the solar system are thinking in terms of. And so that difference matters if you're really concerned as to whether the sun is formed at the same time as the meteorites or formed earlier. So that is an example of the simple ways in which Kumar and I both like to think. And as I say, I finished up with Kumar's first love, namely trying to understand sunspots. Kumar, as we all know, is a wonderful man. I've known him for 37 years. And he has spent all his life thinking in these kinds of terms. I mean, he's done more standard things to write papers, of course. But these are the ways he's been thinking. And I admire him for that. And we should all admire him for that. He was a wonderful man and we miss him tremendously. Thank you.
Okay, thanks for the wonderful talk. So now we have a few questions, so I will take some of them. So the first question from B is the change in gravitational constant merely a numerical manipulation to fit the data, or has it got a more fundamental reason to do so?
Oh, there are various physical theories. Dirac, for example, had one in which it's a fundamental thing. The actual value of the coefficient I chose just to make the luminosity of the sun look constant over time. That was purely numerical, just to show that it can be done. But I hope I showed that when you do that, the age of the sun is substantially less than the age of the oldest meteorites, and so therefore one would rule it out.
Okay, thank you. So now we have one more question. So This is the, of course, they're asking how are the ages of meteorites determined? That is John Sunil.
Oh, they're determined by the decay, radioactive decay of elements within the meteorites, different isotopes of the same element, that element presuming to be in some standard form at the time the meteorite was formed, then if there are different ways in which it can decay, that occurs on different timescales, and therefore you find an age for the meteorite that it makes all those timescales agree.
Okay, thanks.
And it's extremely precise, very precise. I don't quite know how accurate it is because I'm not in that subject. But in most branches of science, accuracy is usually not quite as high as precision.
Okay, so one last question is the seismology of other stars in the universe possible? That is from.
So I didn't hear that question.
Is the seismology of other stars in the universe possible?
Oh, yes. It's being done at the moment. A very large number now. There are spacecraft that have been measuring oscillations of the stars. Kepler is the principal one at the moment. But you cannot do it as well as you can for the sun, because for the sun, we do it for a wide range of degrees of spherical harmonics, and they can be measured by looking at how the oscillations vary across the image of the sun. For other stars at the moment, almost all of them look just like points. And so all we can measure are the very lowest degree modes. We can't actually measure the degree directly, but we can sort of infer it from the frequencies and the theory of how modes of different degree have frequencies that form certain patterns. Some of those patterns are difficult to unravel, but and so we're not quite sure, but others have gone a long way to getting it in a fairly secure way. And so some very important constraints have been put on the structures of other stars, yes, but none of them have had anything measured as a function of radius in the way that we've been able to do for the sun.
Okay, thanks for the talk. So now we'll move on to the next talk. So that is by Professor Shravan Hanasoge from TIFR. So he is a heliosismologist in population 1 because he has only recently started, and recently means some decades ago, unlike Douglas who started 5-6 decades ago. So, and he has, so Shravan is actually an aeronautical engineer by training, and he did his PhD from Stanford, and he is also at an adjunct position in the New York University at Abu Dhabi. So Shravan.
Thank you very much for inviting me, for giving me the privilege to deliver this lecture. We begin by the picture of Professor Chitre. We organized a conference for him a few years ago, so there he is giving a talk. A very, it's really quite an impressive person to speak with, and it's only now that, at this conference, for instance, that I've increasingly realized how distinguished he is, in the station of all the other speakers here. And certainly a privilege to be giving us a talk here. So let me begin. So the goal of my talk is to describe to you how we are pushing the frontiers of precision physics of the sun, and it all comes down to what is it's a function of the data that's available at a given time. And so what was considered precise a few decades ago is certainly is very different than what it is now. And as I say here, the theories and techniques that we develop are broadly, I mean, of course, there are people who are ahead of their time, but broadly are in some sense in proportion to the type of data that are available. But things are now very different because we have extremely impressive space-based observations and very long time series and so on, ground-based as well. And so there are lots of things that we can do now that we couldn't do a few decades ago. We have extremely powerful computing, almost trivially available. And so the question is, can we improve our theories and models to try to understand the sun better? And it's not merely a question of, oh, can I add an extra digit in precision? These types of analyses provide us profound insight into solar physics, into the structure and dynamics of the sun, which in turn will help us understand stellar physics better. One of the most important questions about the sun, which has important stellar physics implications and broader astrophysical implications in relation to the transport of angular momentum in stars, is the question of differential rotation in the sun. And so here in this little picture, I've shown you the actual inference using seismology of the differential rotation of the sun. These are rotation contours of a constant rotation. And this y-axis, the vertical axis, is the axis of rotation. This is the normalized solar radius on both axes. And you would expect what is known as, very popularly known as the Taylor-Krugman balance, that in a rotating spherical fluid, things should align cylindrically parallel to the rotation axis. That simply doesn't seem to happen here. In fact, the contours, as you can see, are distinctly not are lifted away, deviate away from this cylindrical rotation profile. This is one of the monumental and extremely important inferences of 3D seismology, and it's a result that has puzzled us for decades. We still don't have a clear answer as to how the sun does this. And now that we know other stars also appear to do this, we don't know how this works and what the universal mechanism seems to be a universal mechanism that creates differential rotation. A recent discovery, as I said, with more and more sophisticated seismology, we're able to detect better and better things, accuracy and precision in the sun. Is the Rossby waves, which have long been theorized to propagate by the most famous paper in astrophysics being that of Papalouizou and Pringle, who spoke about Rossby waves in the spin down of neutron stars. But of course, there's no reason why a spherical object like the sun can't host Rossby waves. And indeed, so we observe them very strongly actually in the data, in the seismic data. Even non-seismic data appears to show it quite strongly. What's astonishing is no numerical simulation of the three-dimensional convection of the sun, of which there are many very sophisticated and expensive calculations. None of them appear to suggest the existence of Rossby waves. Somehow the sun's convection zone and the dynamics of the sun operate in a completely different regime than is being simulated, than our quote-unquote sophisticated understanding of the sun implies. So that's a major question. There are only specific types of Rossby waves that appear in the observations, and we don't understand why that is. The Rossby waves are very important because, they're very important in atmospheric dynamics. Mike McIntyre, who's also at Cambridge, worked extensively on the transport of angular momentum and the creation of zonal acceleration due to the generation and dissipation of Rossby waves. So it's very important to understand in a detailed dynamical sense as to how the sun is rotating, why the sun is rotating the way it is. An important connecting concept or physics is that of convection. And as I said, there are some extremely expensive calculations, three-dimensional calculations that attempt to simulate convection. So what you're seeing here, for instance, in the upper panel, is a 2D snapshot of a spherical, global spherical simulation of convection. This is near the surface of the upper boundary of their calculation, and the lower panel is the lower boundary, and you see all these beautiful features. Flows appear to go upwards in the centers of these Rayleigh-Benard-esque type cells, and seem to go down in these sharp downflow lanes, the dark lanes in between. We now think, based on all the evidence that's available, that the sun looks nothing like this at all in the inside. So while the numerical simulations appear to suggest this, there's no evidence at all to suggest that the sun is actually doing this. And why that is so is simply not clear. What are numerical simulations missing is again a puzzle, because these are not trivial calculations. So some basic ingredients and some fundamental ingredients are being missed. An important part of the total angular momentum balance picture in the sun is that of meridional circulation. And so this little cartoon here explains how fluid is transported from the equator, goes to the pole, and comes back down. In this particular cartoon, there are two cells. There's one at the surface, and there's something that is slightly in the deeper in the interior. Increasingly, again, seismological evidence suggests that there's only one cell. But whether it's one cell or two cells might appear a detail to you, but it's actually extremely important for maintaining and regulating global solar magnetism. So again, for all the observations and all the time, all the hundreds of thousands and millions of hours that we've spent observing and thinking about the sun as a community as a whole, there are simply some very basic concepts that we don't understand. We don't understand how the sun generates its magnetic field and why it maintains this 11-year cycle, where that number even comes from. I mean, there are theories, of course, there are many theories, but in terms of solid observational evidence to support why that number, why 11-year cycle is not yet clear. So I want to say now, get into the bread and butter, my bread and butter. I'm a helioseismologist. And so what helioseismologists do is image the interior of the sun using observations of the surface velocity field, which basically is the only way by which you can actually say something about the interior. So here is a little video that shows Michelson Doppler imager, which is a satellite space-based instrument that's looking at the sun from L1. And you can see this little, you can see the static here almost as if on a TV. And those are the global solar oscillations that are being continuously excited by turbulent convection. And so these oscillations form, as Douglas was saying, form resonances. So they propagate into the interior, they're deflected away from because of the rising temperature and the increasing sound speed. And so they're trapped in different layers and they form these resonances. And by sort of using different modes, you can image different parts of the sun in theory. So I'll explain to you a little bit more about what that is. The fundamental measurement of the sun is this wave of which we have nearly 2 decades, actually 25 years almost, of continuous observations, is the surface-based Doppler velocity field. Surface Doppler velocity field. And there's a time series and there's a spatial on the disk, right, as in latitude and longitude. So we have, it's 3-dimensional in that sense. You can transform this into spherical harmonics. L is harmonic degree, M is azimuthal order, omega is temporal frequency, written for simplicity as a superscript here. It merely indicates functional dependence. And so this is the basic unit measurement that goes into helioseismology. And using various forms of these, you can interrogate the interior. So the seismology, in a broad sense, is a study of the spectrum of the wave operator. So we know, for instance, in the sun and likely all other stars, that linear wave physics or linear theory works really well for waves. They're small amplitude waves, i.e. the other dynamics, at least in the interior, are happening on time scales and spatial scale, or not spatial scales, but temporal scales. And in terms of amplitude, they're very different. So these are small amplitude waves. And the scale separation in time allows us to use the waves to image what's happening in the sun, because the waves they have periods that are much faster than the periods of evolution of various aspects of the sun that we're interested in. And so what do I mean about the study of the spectrum? So the spectrum of a wave operator, in this case, it's a self-adjoint or it's a symmetric wave operator. So it has a complete set of eigenfunctions, it's a complete basis, and has eigenfrequencies. So there's eigenfrequencies, and then there are speaking about broadly in the previous talk was eigenfrequencies. Eigenfrequencies make the most sense in it makes the most what shall I say, intuitive sense, because we understand the frequencies of resonance, right? So you tap a little metal sphere and you hear a sound, and you know that these can comprise the resonant frequencies of that ball. What's more complicated and abstracted is the eigenfunction, is the study of the eigenfunction. And so eigenfrequencies, as it turns out, are extremely powerful. They give you extremely powerful information, but limited by the fact that they're dominantly sensitive to axisymmetric, north-south symmetric, very, very symmetric features. So things like rotation, things like the first order structure of the sun, what is the sound speed is a function of radius, and so on. So these are the aspects that eigenfrequencies give you information about. But if you want to try to understand the non-axisymmetric parts of the sun, which are truly quite interesting, and as I was saying, it profoundly affects like convection, for instance, and so on, which give you insight into angular momentum transfer and these deep questions. Those simply are not possible to study those with eigenfrequencies. So eigenfunctions then is what you use for those. And so the basic idea of what is known as mode coupling. Mode coupling is a very well-established technique in geophysics. It's been around in helioseismology for several decades, but very, very minimal, but we've seen very little application of it. And so the idea is that you have a reference model. Generally, you assume the reference model is a very good approximation to the sun, and it is. At its heart, helioseismology is a perturbation theory. And so, so you assume that the reference model is non-rotating, it doesn't have convection, it's axisymmetric, it's non-magnetic, as this says. The sun, of course, is doing as it wishes, and it has all of these other aspects that we ignore in the reference model. And the reference model has its set of eigenfunctions, which, as I said, for the self-adjoint operator, the linear wave operator, is orthonormal and complete. So every eigenfunction of the sun can be written as a linear combination of the eigenfunction of the sun as a linear combination of the reference eigenfunctions. And there are these weights. These weights are coupling coefficients that couple. This is what we call coupling coefficients. You know, every k, as the index k is connected to a k prime index here. So that's the basic idea. And it's a really beautiful measurement because you can only observe the surface. You can't observe the interior of the sun. So really the only thing that you can study is the departure from spherical harmonics. So we assume, for instance, in the reference model that all the eigenfunctions are spherical harmonics. So every mode has a unique label, Lm, and you know, of course, it's a radial order as well, but the radial order is not really relevant for the discussion here. We can't really see inside the sun, so we can only see the surface. But those indices L and M assume basically that your data are perfectly you know, can be projected onto spherical harmonics. But spherical harmonics are in fact not the correct basis because you have the wave operator contains all these non-axisymmetric terms that are changing your eigenfunctions. And so you can measure the departure from spherical symmetry of the eigenfunctions themselves, so departure from spherical harmonics. And the way you do that is the two-point correlation function in the spectral domain. You can ignore all of these terms. This comes from some laborious theory that you can do. This is a theoretically derived weight function. And these coupling coefficients that I spoke about before is basically linearly connected to this two-point correlation function in the spectral domain. And you see that I'm correlating two different frequencies. And so this corresponds to a time-varying perturbation theory. So things are varying as a function of time on time scales 1 over sigma. And they're varying as, this can also be L prime. So things are varying as a function of space as well. They're spatially heterogeneous. And so this two-point correlation function then tells you how much of a departure from spherical harmonics a certain measurement or you know, the eigenfunction of the sun is. And you can write you know, as an elaborate inverse theory that connects your measurements, this coupling coefficients basically, to flows in the interior, so to various motions in the interior. This is a poloidal motion, this is a toroidal motion, and then you have Lorentz terms that come from magnetic coupling and so on. So you have the full sensitivity of this. It's extremely sophisticated method for, you know, because it's very simple to do. It's very easy to set up. It's a very rigorous foundation, very mathematical. There's not a whole lot of data manipulation, which is actually a very important thing in my opinion. And it's been validated quite a bit now. Differential rotation and Rossby waves have been detected using this method. And so there are 2 or 3 things that I want to describe here and that I thought was particularly interesting. So differential rotation is often thought to be, as I said, the most important and one of the most robust inferences from helioseismology. So it turns out it's not quite right because again, it all comes down to the basic premise. All the inferences of differential rotation assume that you have that spherical harmonics are the eigenfunctions, right? So that every mode that you observe, that's oscillation mode, has a unique L and M. L and M are its correct indices, but they're really not. So a mode is not a mode by itself, but rather a collection of modes that are speaking together. So it's because the eigenfunctions are not individual eigenfunctions that are cleanly separable in the spherical harmonic basis. The basis in which you separate these eigenfunctions is different from spherical harmonics, is what I'm saying. So if you take that into account, if you take that these elaborate physics known as quasi-degenerate perturbation theory, so if you take that into account, you will see this particularly A3 and A5 are of relevance here. A3 is in a sense the degree of differential rotation of a certain component of a certain extent at the surface. A5 is again a differential rotation measurement at the surface. It's in nanohertz, small. thing. And what you see here, these are the blue and the yellow here are error bars. And you see that this is the error in between quasi-degenerate perturbation theory and degenerate perturbation theory. So this is the error that we are making right now in our inferences of differential rotation. And this is from a small data set. So if you improve the length of your time series, the error bars fall significantly. So we're well out of the error bars here. So as we've started doing different inferences of differential rotation, we've already found notable differences in the surface layers. So by doing the theory more carefully, this was not considered, as I said, this was not considered precise or accurate. I mean, or rather, it wasn't important. This difference is so tiny. We're talking about 0.05 nanohertz and so on. Was not considered important, 10 years ago, 20 years ago. But now, with our precision data and high precision measurements and so on, we can powerful computing, we can actually improve, use more sophisticated theory to try to explain these differences. And similarly for A5 as well. Once the error bars come down, you can start to see that there's a statistically significant shift. Okay, so that's one aspect of it. Now on to non-axis symmetric features in the sun. So what I'm plotting here is a sectoral mode of Rossby waves. So the horizontal axis is azimuthal degree equal to harmonic degree equal to azimuthal order, and the vertical axis is the temporal frequency in nanohertz. So this was observed a few years ago using helioseismology. This here, you see this very clean feature that, with high signal to noise. This is a Rossby wave. So we know the dispersion relations of Rossby waves in a spherical fluid. They're known as Rossby-Horowitz waves. And so you can match this observed power here along this path with the theoretical curve, and they match very accurately. So basically, you can measure these things very well. And an important question, as I said, is the generation and dissipation of these Rossby waves, because that's very critical to the transport of angular momentum. And so it turns out, astoundingly, actually, I was really astounded. So the mode coupling is still, despite its prevalence in the field for 3 decades, it's simply not been studied very carefully. But despite that, my initial analysis shows that here is a different technique in helioseismology here. This is known as ring diagrams. This is known as time distance, a different, both ring diagrams and time distance are frequency measurements. They are the temporal measurements. They're looking at changes in time or frequency of modes. And this, the black line is the eigenfunction measurement that I was describing to you earlier, called mode coupling. And so this is a signal to noise ratio versus harmonic degree. So it's the same as the harmonic degree here. And note that each of these modes is observed with a certain signal to noise. And what's astounding is at some of these, for instance, the signal to noise of mode coupling is nearly 100 times that of time distance. And there are reasons why these are small. These are smaller than can be. And it needs improvement. But this astounding improvement in signal to noise gives us hope that, just to say, signal to noise of 10 means in 1 year with mode coupling, you can observe as much with as much signal to noise as you could with from 100 years in time distance, right? This is square root of n time dependence. So it's a really extraordinary improvement in signal to noise. And this gives us hope that we'll actually be able to do other inferences with a much higher signal to noise. And really to try to do deep interior inferences of Rossby wave eigenfunctions and so on, mode coupling is pretty much the only way that you can do it. What do we know about convection? So convection, as I said, is a very important part of solar dynamics. And we know that long-range velocity correlations we think at least, that they drive angular momentum transport and so on. And one of the major questions actually in the sun is why there's a depletion of power in this is a horizontal axis is spherical harmonic degree, vertical axis is velocity. There's a depletion of power here. And canonical turbulence theories tell you that all the power and turbulence rests in the largest scale. So you wouldn't actually expect this power to decrease if the sun were a classical turbulence system. You would actually expect it to flatten or even increase. And so this particular decrease is quite puzzling, and there's a major source of debate in the community. And another thing that we did with mode coupling was to try to measure the geometry of these flows, of these convective flows. And they all appear to be confined. So these are observations, and this is numerical, a very advanced and state-of-the-art numerical simulation. And so you see, in fact, the numerical simulation suggests that power rests outside of the low latitudes, whereas observation suggests that they all sit at these low latitudes. So there's a fundamental difference in between numerical simulations and observations. And this suggests, again, that there are many gaps to be plugged in our understanding. So this particular thing, I want to draw your attention to this peak in the power spectrum. You see this little bump here. These are known as supergranules, and they're L of 120 or so. And they're very mysterious because no one understands why they are there. Their role in thermal transport appears to be minimal. And they're also the transition from what is conventional turbulence at these smaller scales and what appears to be anomalous turbulence at these much larger scales. So what is happening in these transition region, and so on. One of the important questions is how deep these supergranules go, because the moment you know how deep they go, you know what driving mechanism is pushing them or is creating them, and so on. And so that's a very important question again. And again, we use mode coupling here, which is incredibly straightforward compared to other conventional helioseismology techniques. And I don't want to get into the details of it, but we find that supergranules are waves. This is what has been known for a while from Gison's paper result 2 decades ago. And in fact, they're prograde waves. So they have greater power in the prograde direction. The horizontal axis here is wave number. Both of these are X and Y wave numbers. So these are much smaller than the sun, than the solar radius, which is why we can use a Cartesian approximation. And you see a dispersion relation, what you would expect basically of a wave. And so this is the result from Langfellner, I believe. And they're all broadly in agreement. And mode coupling is also, and the reason why I'm showing this is that with trivial effort, we're able to get at all of the major questions that remain in the sun, including supergranulation. And signal to noise is probably much better than all these other methods. And and we're able to basically replicating all of these results, which are sort of known as standard candles now in the field. And so I'm nearly close to wrapping up. So I just want to discuss 2 or 3 more things, and then I finish. And so meridional circulation, as I described to you earlier, is extremely important. And one of the questions of meridional circulation is what happens deep in the interior.
Shravan, can you wind up first?
Yeah, I'm done. I'm basically done. This is the deep interior. This is close to the base of the convection zone. What happens here is of great consequence to dynamo theory and how solar magnetism is generated. And so we believe that our signal to noise could be as much as 10 times higher than other methods. And we can also think that we can do a better systematic error, center to limb as it's known, and therefore infer these flow velocities, the deep interior, much better. So the last couple of things that I want to say is that a major outstanding challenge in the sun has been whether G modes exist, which it's generally assumed that they do. These are internal gravity modes. And if they do, can we detect them? And so there have been a lot of efforts in this regard, but no luck so far. And so we think that with mode coupling, it may well be possible with a boost in signal to noise and so on, that we can place, if not detect them, place extremely tight constraints on the amplitudes of these gravity modes. So that's it. This is my last slide. So we've benchmarked against standard candles that are widely accepted. And now we believe that we can make really significant contributions to understanding a broad range of essentially all the fluid dynamics of the sun that we think is important: convection, Rossby waves, differential rotation, meridional circulation, and gravity modes. So on that note, I just want to say that many of my students in India, abroad, and collaborators and so on, have all contributed significantly to this ongoing effort. So thank you very much.
Okay, thanks for the wonderful talk. So now we have a few questions. So one question from Prasitosh Day is that why can't the eigenfrequencies be used in the case of non-axisymmetric analysis?
There have been attempts, but to leading order, they're sensitive to axisymmetric perturbation. So if you wrote a perturbation theory and you said, well, if I had an axisymmetric perturbation plus a non-axisymmetric perturbation and so on, you would find that to leading order, they're sensitive only to axisymmetric north-south symmetric perturbations. So you can't even use normal the eigenfrequencies to detect meridional circulation. Sorry, I'm done with the answer. Just for sure. You can't use normal modes eigenfrequencies to detect a feature like this. This is axisymmetric, but it's north-south antisymmetric. So to leading order, the eigenfrequencies are not sensitive to this. There's lots of other stuff that's, yeah, so you can't see it.
Okay, so the other question is, what is the physical interpretation of eigenvalue and eigenfunction in the context of wave phenomena? That is from Muhammad Naeem.
It's just if you take a little metal ball and you hit it with a spoon, you hear a sound. That's the eigenfrequency. And if you could actually observe the rattling of the surface of this of the sphere, then that's the eigenfunctions. And if you could see in the interior of this ball, then I would tell you as a function of radius what the eigenfunction is and the motion of the ball.
Okay, so one last question is, it appears that heliosysmology has a lot of experimental data, but not enough theoretical understanding of the said data. So is that true? It's from Saif Khan. No,
that's not true. We have a very good understanding of this, but we're constantly still making progress. There are challenges. It's not to say that we don't understand. We understand a lot of things very well, but there are things that we still don't understand, and we are definitely making progress.
Okay, so thanks for the talk. So now we move on to the last talk. So this is by Professor Sarbani Basu from Yale University. So she is in my definition, the top 2 of the heliosysmologists, because that I define as the people who started working around 1990, because that was the time when the first extensive database of the frequencies were published, and it was only after that that a lot of progress was made in heliosysmology. Of course, many important results were obtained before that, but it is the decade after that which was the golden decade of heliosysmology. So she just started working around that, and of course she was also a student at TIFR, and she is also a recipient of the Hell Prize. So now I invite Sarbani Basu to give her a talk.
Thank you very much, and thank you for this opportunity. So I'm particularly pleased to be able to talk in this session because Professor Chitre was one of the 3 people who made it possible for me to have a career in heliosysmology and be where I am today. And when asked to speak, I decided to speak on dynamics because I've had a couple of papers on solar dynamics where Professor Chitre was a co-author. These 2 papers, we call them the ABC papers because the authors are in that order. And what I'm going to talk about today is mainly what we've learned with the lot more data that we have. Now, Douglas and Shravan set a bit of the stage for what I'm going to talk about. But I'd like to still go back to the basics slightly. For that, how do we peer into the sun? And that's seismology. Okay. And all these modes are basically generated by the convection zone that Shravan is trying so hard to study. My job is easier because I just use the eigenmodes to find dynamics. And what basically I'm going to talk about today is not so much the dynamics, but how the dynamics changes with solar cycle. Okay, so let's start at the beginning. We talked about spherical harmonics. So what is it? So we define each mode. We're talking about normal modes. I'm going to just use normal modes here. We define each mode by 3 numbers, n, which is the number of nodes in the radial direction. And for the surface, we use spherical harmonics. So L, which is the degree, is basically the number of nodal circles on the circumference. And M, the azimuthal order, is the number of nodes crossing a latitude. So it's the number of nodes along the equator, so to speak. Now, if the sun were spherically symmetric, that means it did not have rotation or magnetic fields, all modes with the same L and N would have the same frequency, okay? But rotation lifts this degeneracy. Think of it, for those of you who are used to quantum mechanics, think of the Stark effect or the Zeeman effect on the energy levels of hydrogen. It's, in this case, it's rotation that breaks degeneracy. And it splits the mode so that the frequency becomes M-dependent. And the way these M-dependent frequencies are related to the internal rotation is given by this equation. That's the difference in frequency for the different M's. Can you see my cursor? I hope you can.
Yes, we can see.
Okay. And basically, it's an integral over the kernels of the rotation, which are known functions, if we believe the theory, and the internal rotation rate. Now, in the case of the sun, we observe modes to a very high degree. Well, at least for global helioseismology, it's done with degrees of up to 250 and sometimes 300. So you can see you would have way too many frequency, way too many splittings. And when you go that high in M, the signal to noise reduces. So instead of using the splittings are converted into coefficients of splittings so that you can you can express the frequency as a frequency that depends on the spherical symmetric part and splittings caused by anything that lifts spherical symmetry. And in the case of rotation, it's the odd order coefficients that matter. So when Shravan was showing graphs with the A4 and A1, that's what he was showing. It's the splittings converted into splitting coefficients. The HMI and MDI project usually give us splitting coefficients up to 836. And given the nature of the data, there hasn't been any need to go higher in that. It gets very noisy beyond that. Okay, the reason we can do so well is the precision of the data. So this is the degree L, this is frequency in millihertz. That's, I think, a one-year data set from the Michelson-Doppler imager. These are 1,000 sigma error bars. And that's why we get the precision. And recall, I'm talking about precision. We think we are accurate, but who knows? We hope we are accurate, but we're definitely precise. So in the solar rotation profile, Shravan talked a bit, but I shall go through it. This figure by Klatzmeier shows the rotation contours that we had expected to find in the sun. Simple Taylor columns with the contours being parallel to the rotation axis. Instead, what we see are contours that are almost radial, they're not quite radial, up to the base of the solar convection zone, which is marked in this dashed line. And beyond that, we really have no sensitivity. And beyond that, it's more solid body-like. The white regions are where we really don't have much sensitivity, which is a pity. In evolved stars, where we have some data now, because the nature of the modes is different, we actually know the rotation rate of the core better than the rotation rates that we know for the sun in the core. Quite ironic, I would think. Again, in the poles, we do not know what's happening. We lose sensitivity. I'll come back to the poles later in the talk if we have some time. Now, a bit more detail. Now, instead of showing contour plots, I'm showing cuts at different latitudes. So we start at 0 degrees. The blue line here is 30 degrees and the green is 75. And you can see that there are two main features. One is the sharp change. Actually, the change is sharper than what's shown in this figure because these inversion results have a the resolution at that point is not, the radial resolution is not very good. This is what's known as the tachocline, and with the common consensus, doesn't mean it's correct, of course, is that this is where the main solar dynamo resides. So the properties of the tachocline are very interesting. The other region, which is a bit of a mystery even today, is this change, this sudden increase in the rotation rate very close to the surface. This is known as the near surface shear layer. Now, if you believe simulations of rotation, to form a tachocline, you need an entropy gradient in that region. The question is, what causes the entropy gradient? The near surface shear layer is a bit more of a mystery, because most simulations of solar dynamics actually ignored this region, because this is the region with highly compressible turbulence, and the anelastic approximation that is used in simulations breaks down here. So, which is why normally most solar simulations for rotation start at 0.95 solar radius and go below, instead of the surface above is not generally simulated, except there is an old paper nearly 20 years ago by Frank Robinson and Quinn Chan, where they just do the surface fully compressible, and they seem to see a near surface shear layer, but we do not understand it, or for that matter, what role it plays. There are hypotheses saying that there could be a second dynamo there. Okay, why do we want to look at changes with solar cycle? Solar frequencies are known to change with time. Now, Shravan mentioned 25 years of solar data. Actually, there's even more, because the Birmingham solar oscillation frequencies actually even have data for solar cycle 22, but these are sun as a star data, so low degree data. And if you follow the frequency changes, these are marked by the points with the error bars, you can see a nice up and down, up and down, up and down. And what's marked in red are various solar activity indicators. So this particular plot is with the sunspot number. The one below it is the 10.7 centimeter radial flux. And in general, the frequencies follow the activity indices, except not completely well. This is something we need to keep in mind. And there are some indices, like the interplanetary magnetic field, cycle 22 was fine, cycle 23 and cycle 24 don't seem to follow it at all. Something to be kept in mind, but nonetheless, you can see that frequencies change with time. Frequency splittings change with time too. This is just for cycles 23 and 24. These are frequency splittings averaged for those that only probe fairly close to the surface. So the different colors are different measurements. So black is gong, blue is MDI, red is HMI. So you can see there's a bit of a systematic difference between measurements, but that's not what I would like you to look at. What I would like you to look at is the time variation of these splittings. And unlike frequencies, they do not just simply rise and fall with the solar cycle, which means we're probably going to see very, very interesting solar cycle related changes in dynamics. What do we know? Okay, we know that the average solar rotation rate over solar cycle 23 was different than that for solar cycle 24. And this is what is plotted here in meters per second. So this is the velocity, not the rotation rate. So there was this change. It's a fairly significant change. I haven't plotted the error bars, but they're very small. Now, what is normally done is to look at what's known as zonal flows. You take the rotation rate at any epoch and subtract from it the average rotation rate. And this is shown in this figure for various depths. The panel to the left is for GONG. Panel to the right are the space-based data, MDI and HMI. This is cycle 23. This is cycle 24. And what do we see? Cycle 20, we see these migrating flows in the at solar minimum. This is about the minimum before solar cycle 23. This is the minimum between 23 and 24. The flows move from the mid-latitude regions to the equator, and there's a prograde branch which goes from the mid-latitudes to the pole. And interestingly, cycle 24, the flows have been very, very weak compared to that of cycle 23. And for those of you who are interested in cycle 25, which we are now already in, you can actually see the beginnings of cycle 25, even within cycle 24. So in terms of solar dynamics, we see the onset of the next solar cycle long before the first sunspots appear. Now, this is a function of latitude on the y-axis, time on the x-axis at different depths. This can be plotted as radius on the y-axis, time on the x-axis, but at different latitudes. And it almost, you can think of them as, say, at 15 degrees, flows rising from the base of the convection zone, which is 0.7 solar radius, from the solar minimum, and at low latitudes reaching the surface at solar maximum. So these are really complicated patterns. We don't quite know what is going on. We don't know completely what is driving these changes. But perhaps an even more interesting point, which is we first made in the paper where Professor Chitre was a part, this is we first showed this in 2008, that sunspots emerge in this low latitude prograde band of the zonal flow. So the top figure is MDI and HMI, low figure is Gough. I've only shown the points in one just for the sake of clarity. The vertical dark lines show the position of the solar maximum. Now, even more interestingly, the emergence of the sunspots is where the gradients of the flows is the maximum. So we don't understand how sunspots emerge, and we don't completely understand why zonal flows do what they do, but clearly there is a relationship. The question is, are the shears in the zonal flow affecting sunspot emergence, or sunspot emergence affecting zonal flows? I mean, most likely, given that life is never simple, it's a complicated feedback loop, but again, it's one of the mysteries. I'd like to come to the tachocline now. This is a schematic of the tachocline, because the tachocline is characterized by this change in the rotation rate between the convection zone and the radiative zone, a position, and a width of the change. Now, I'll only concentrate on the change in the rotation rate because that's the only one where we see any significant solar cycle related change. Now, just for reference, I've plotted the base of the convection zone with the vertical gray line here. So we looked at whether there is a change in the rotation rate across the tachocline as the solar cycle progresses. And the answer is definitely. This is the change at the equator. In the background, I show you the sunspot numbers so that you can orient yourself to the phase of the solar cycle. But what is interesting is that it's a much more complicated relation with the solar cycle than a simple correlation with it. So the interesting question to me is, say, 15 degrees or 45 degrees, is the tachocline following a solar cycle, solar sunspot cycle, which is 11 years, or perhaps a solar magnetic cycle, which is 22 years, or perhaps something even longer? So I'm hoping the next few years, we are already in cycle 25, will let us know whether, say, at 15 degrees, this rate is going to start falling again, or at 45 degrees, it's going to start rising again. And equator, of course, I have no idea what this periodicity is. Now, the difference between cycle 23 and cycle 24 was actually a bit more fundamental, because even at the same level of activity, so I've plotted the same jump in the rotation rate now as a function of the 10.7 centimeter flux, the black and the red of a cycle 23, the purple and the blue of a cycle 24, and even at this, interestingly, there's a hysteresis effect. You can see that, but it's a magnetic field related effect. Hysteresis is, I imagine we should expect that. But what perhaps is more interesting is that even at the same level of activity, the jumps have been different. So whatever is causing the tachocline to change, maybe it's the tachocline which is changing the surface, who knows? It is not directly related to the solar cycle indicators that we use. We always use surface or chromospheric or even coronal activity indicators. So this, to me, is one of the mysteries that we still have. Let me get back to the poles. We do not observe the poles very well. Global helioseismic data loses sensitivity. And local helioseismic data also loses sensitivity because of foreshortening of the Doppler images, because we are looking from the ecliptic. Nonetheless, we can try to do something, and these are ring diagram results of what we called flow anomalies. That is, we found the flows and subtracted the mean flow from that, close to the pole. If I recall correctly, that's the South Pole, that's the North Pole, or maybe it's the other way around, it doesn't quite matter. But you see the white bit in the middle? That's the part we don't see at all. The reason the white bit gets smaller and larger is because, fortunately for us, the sun isn't completely at right angles to the ecliptic. It has a tilt of 7.5 degrees, so we can go closer to the pole at some points, in which case this unknown region gets shrunk. Now, solar orbiter is going to observe from a latitude of 30 degrees, so it should get the poles a bit better. But the solar orbiter is going to only observe the pole for 10 to 15 days, which will allow some helioseismology, but not too much. I'm a part of a proposed NASA mission called Solaris. We are in a phase A study right now, where we plan to observe the solar poles from the pole. So there'll be passes over the solar North Pole and the South Pole, and we would be able to keep the pole at relatively low inclination angles for nearly 3 months. 3 months should be a good enough time to do both local helioseismology and answer questions like, what does the solar differential or solar rotation look like in the pole? Does the solar pole have these beautiful vortices like the one the Cassini spacecraft found on Jupiter, for example? The nature of the vortices tell us about what type of convection we have, because it's the interaction of convection and rotation that, in some sense, provide the length scale of the vortices. And that can hopefully try and narrow down some theories of the solar dynamo. So it's going to be exciting. We are in phase A. We are just putting it in the proposal for phase B. We hope we'll be selected for the phase B study, in which case we can figure out exactly what we need to do to study the poles. But the poles are basically unknown regions of the sun when it comes to dynamics. And yet they might tell us what sort of solar dynamo regime that we actually reside in. So I'm going to just leave you with a few thoughts. We see solar cycle related changes in the internal dynamics. Whether we understand them is a different issue. I don't think we do. The change in the dynamics in solar cycle 24 was very different compared to 23. And the changes do not have the same correlation with solar activity. And as I mentioned, perhaps solar cycle 25 will shed some light on this, or maybe it'll make our lives even more difficult. And so we need to continue monitoring the sun. The Gough is doing a good job. There are proposals to have a new generation of Gough. The proposal has been submitted to the National Science Foundation last month. That is going to allow us to continue the ground-based work. Space-based, there's a question mark after the Solar Dynamics Observatory, but let's see what happens. So thank you very much for your attention.
Yeah, thanks for the nice talk. Now let me ask the host whether there are any questions.
Yes, I texted you. I sent it to you.
Okay, yeah. Yeah, so the question is, how does the composition of the sun vary over depth? And zooming in on the surface, could this result in sunspots when combined with the flow? So I don't know who has asked this question. But
composition, do you mean chemical composition?
I suppose so. It is chemical.
Yeah, so, okay. I find it hard to think that chemical composition would do anything, because given the amount of elements that actually react with magnetic fields is very small. Yeah. Also, why would the composition change with time? The only way a composition...
Sorry, no, not asking about time. He's asking about vary with depth.
Oh, okay. So yes, of course it varies with depth, but not in the convection zone. The convection zone mixes very, very quickly at timescales that are way shorter than a solar cycle. So it cannot do a solar cycle related change. Yes, it varies with depth. Composition is constant up to the base of the convection zone. Then it changes. For example, you'll have an increase of helium and heavy elements because they have settled down under gravity over the last 4.5 billion years from the convection zone to the interior. And of course, in the core, nuclear reactions have converted hydrogen to helium. So yes, there is a clear depth dependence of chemical elements, but that is unlikely to change on timescales we're dealing with.
Okay, so the next question from Arush Murali. Anomalies seem to increase in strength near the poles. Could this be due to the reduced device sensitivity, or could it provide new insights into the heliosysmology?
Okay, let me go back to that figure. This projection is such that you're going to see the poles better than the equator. So unlike usual projections where we look at the equator as the center of the field, we've done a projection where you're looking straight down on the pole. But of course, the errors on these flows are pretty large. So whether the flows are stronger at the poles than the equator, they're not really. It just appears on this figure because of the projection. But the errors in the flows close to the pole are larger than that at the equator because of the reduced sensitivity.
Okay, so I don't see any more questions. So let us thank all the speakers of this session, and I will hand over the session to the host.
Okay, let me thank Professor Antia for chairing this session. So we'll close now and we'll come back at 6:30 for the last session of the day. Thank you.